Okay, in this lecture, we're going to continue with our section 2.5 material on physical applications of the integral. And in this lecture, we're going to consider determining how much work it takes to lift a rope or a cable, maybe up the side of some building, or if we're pulling, say, a bucket of water by means of a rope up from the bottom of a well, how much work would be required. So these types of problems I'll refer to as rope or cable problems. And let's look at an example to illustrate how we're going to find this work required. So in this first problem, we're given a 40-foot rope, which weighs 6 pounds per foot, is hanging over the edge of a 50-foot building. And at the bottom of the rope, there's a bucket of rocks, which weighs 100 pounds. So the question is, how much work is required to pull this bucket of rocks to the top of the building? So let's start by illustrating the problem that we're working with. We have a 50-foot tall building, and over the edge of this building, there is a 40-foot long rope. And we're told at the bottom of this rope, there's a bucket of rocks, which weighs 100 pounds. And the question is, how much work would it be required in order to lift this bucket to the top of that building by means of this rope? So in order to determine that work, we're going to approach the problem in the following way. Let's suppose that we have a small section of rope. So let's think about slicing this rope up into small pieces of a length dx feet. So these little small sections that we're going to take will be of length dx measured in feet here. And I'm going to determine how much work is required to lift this one little segment of rope to the top of the building. Now, a little notation I'm going to use here, the work required to lift this section of rope depends on the distance of this section of rope from the top of the building. So I'm going to let x, measured in feet here, denote the distance of my little section of rope from the top of the building. So let's see if we can determine the work required to lift this one slice or this one little section of rope to the top of the building. So here I'll say the work required to lift this segment of the rope is what I will call a differential of the total work W to lift all of this rope to the top of the building. And let's think about how we could calculate this. So there's two things I need to determine work. I need the force required to move this section of rope, which would be equivalent to its weight, and then I need the distance traveled, the distance that section of rope will travel to get to the top of the building, which we've already labeled as x feet. So let's think about how to get the force required to move this section of rope. Now in the problem statement, we're told that this rope weighs 6 pounds per foot. So to get the weight for my section of rope, which would be equivalent to the force needed to move it, I'm going to take my weight density, which was 6 pounds per foot, and then multiply by the length of that section of rope, which was dx feet. So this will be my weight, 6 dx pounds, and then I have to multiply by the distance over which this force is being applied. That is the distance traveled by that section of rope, which would be x feet in order to get to the top of the building. So I have a 6x dx foot-pounds of work required to lift that one segment of rope to the top of the building. So to get the work required for all 40 feet of this rope, so recall that the total length of this was 40 feet. We're going to add up the work needed for all of these little sections from the top of the rope, which would be corresponding to x equals 0, or x feet from the top of the building, all the way down to the bottom edge of the rope, which would be 40 feet from the top of the building. So here I can say the work for all of the rope would be given by, let me label this W1 for now, and I would be taking the integral of this 6x dx foot-pounds from x equals 0 to 40 feet. So let's see what we have here. Our antiderivative is 3x squared, which we're evaluating from 0 to 40. So we would have 3 times 40 squared, which would be 1600, minus 0 squared, which is 0. So my 3 times 1600 gives me 4800. And here, since everything was being measured in feet and force or weight was given in pounds, then work would be in foot-pounds. And we also need to determine how much work is done in lifting this bucket of rocks. So this 4,800 foot-pounds that we found is only the work required to lift the rope itself, not including that 100-pound bucket of rocks at the bottom. So I could then say the work for the bucket of rocks is what I'll call W2, and to get the work done in lifting this bucket of rocks to the top of the building, I would take the force required to move the bucket of rocks, which is equivalent to its weight, this 100 pounds, and I would multiply by the distance that that bucket of rocks travels. So if it's at the bottom of this 40-foot rope and we lift it to the top of the building, it would travel a distance of 40 feet. So taking our 100 pounds times 40 feet, we get 4,000 foot-pounds of work for just the bucket of rocks itself. So to get the total work, in order to lift this bucket of rocks by means of the rope to the top of the building, we would have the sum of the work required for the rope and the work required for our bucket of rocks, which would give us 8,800 foot-pounds of work required to lift that 100-pound bucket of rocks by means of this rope to the top of the building. So the idea for these rope or cable problems is similar to what we've been doing in our earlier sections for applications of the integral. We're going to think about slicing up our rope into these small segments, calculate the work required to lift that one segment some distance, and then add up the work required for all of those sections over the length of our rope. And then we have to keep in mind, well, if we have some bucket of rocks or something else that's hanging off the bottom of the rope, we have to be sure to account for the work required to lift that bucket as well. So let's look at another one. In this next example, we're told a uniform cable, which is 30 feet long and weighing 120 pounds, is hanging over the edge of a building 60 feet tall. So we've got two parts here. Part A, how much work is required to pull the cable to the top of the building. And in part B, how much work is required to pull 10 feet of the cable to the top of the building. So let's take a look at this. Again, I'll illustrate this. So we have a 60-foot tall building, and we have a uniform cable, which is 30 feet long, hanging over the edge of this building, and it weighs 120 pounds total. So how much work is required to pull the cable to the top of the building? So let me start by labeling the total length of our cable, which was 30 feet. And I'm going to be looking at some little section of cable that is X feet from the top of the building and has a small length of dx feet. So I'm going to determine the work required to lift that one segment of cable to the top and then integrate over the length of my cable to get this total work. But one thing I need here is the weight or the force needed to move my one little section of cable. What I'm given in the problem is the total weight of this cable, 120 pounds. But I'm told that this cable is uniform and is 30 feet long. So uniform here meaning that its weight density throughout is constant. So let's first find our weight density for this rope. So here, our weight density. We were given in the previous example. Here we need to find it. So we have a 120 pound cable, and this 120 pounds is divided equally along the 30 feet of this rope. So we have 4 pounds per foot would be our weight density for this cable. The work for our segment is a differential of the total work for the entire cable, and I would find the force needed to lift that segment by taking its weight density of 4 pounds per foot, multiplying by the length of that segment, which was dx feet. So this gives me the force needed to lift this. It would be 4 dx pounds. And then to get work, we would multiply by the distance this segment has to travel to get to the top of the building, which would be x feet. So our differential of work for this little section is 4x dx foot-pounds. So to get the total work needed to lift all 30 feet of this cable to the top of the building, I would integrate this 4x dx foot-pounds from x equals 0 up to 30. So here we would have an antiderivative of 2x squared. We're then evaluating from 0 to 30. So we would have 2 times 30 squared, which would be 900, minus 0 squared is 0, which gives us 1800. And since force was being measured in pounds and distance in feet, our unit for work here would be foot-pounds. So 1,800 foot-pounds to lift all 30 feet of this cable to the top of the building. Now, in part B, we asked the question, how much work is required to pull 10 feet of this cable to the top of the building? So let's start here. Using the same sort of notation that we were using in part A, we can say the work for the first 10 feet is given by, let me call it W1. And to get the first 10 feet of cable to the top of the building, well, I would be integrating my 4x dx, which is the work required for one little segment of rope of length dx feet taken at a distance of x feet from the top. And if we only want the first 10 feet of cable, we would be integrating from 0 to 10. That is from the section that is at the top of our building down to a distance of 10 feet from the top of the building. So this gives us a 2x squared, evaluating from 0 to 10. So we would have 2 times 10 squared minus 0 squared, which would give us 200 foot-pounds. However, one thing that we have to be a little bit careful of here is when we're lifting the first 10 feet of cable to the top of the building, what we've calculated here is only the work required to lift the first 10 feet of cable itself. But we have a total of 30 feet of cable. So when we pull in the first 10 feet, well, we're not only lifting a 10-foot cable to the top of the building, we're also moving the bottom 20 feet of the cable that hangs off the initial 10 feet of cable, a total distance of 10 feet to the top. So let's visualize that here. If we have our building with a 30-foot cable, and we only have found the work required to lift the first 10 feet of cable to the top, well, we've neglected this 20-foot section of cable that is, we can think of as hanging off the end of our initial 10 feet. So we can't neglect the work required to lift that bottom section of rope. So what we can do here is we can think about this bottom 20-foot section of rope as like a bucket of rocks, which is hanging off the initial 10 feet of our cable, and we need to find the work required for that bottom 20 feet. So let me say here the work for the bottom 20 foot of cable is given by, let me call it W2. So let's think about how much force is required to move that bottom 20-foot section of cable. So its length is 20 feet, and let's think about its weight density. In part A, we said this cable weighs 4 pounds per foot. So the total weight of that bottom 20-foot section of cable would be 80 pounds. And the distance that we're moving that bottom 20-foot section is 10 feet. So in pulling up the first 10 feet of cable, we're lifting that bottom 20-foot section a total distance of 10 feet. So here we would have 20 times 4 would be 80 times 10 is 800 foot-pounds. So to get our total work needed to pull the first 10 feet of cable to the top of the building, we would sum the work for just the initial 10 feet of cable and add the work required to lift the bottom 20 feet of cable a distance of 10 feet, and we see that we get 1,000 foot-pounds. So something interesting that we might compare here is our answers for part A and part B. In part A, we said, well, to pull all 30 feet of cable to the top of the building was 1,800 foot-pounds. However, in part B, just to pull in the first third of that cable was 1,000 foot-pounds, well over 1/3 of the total work to pull in all 30 feet that we found in part A. So why would that make sense? Well, the first 10 feet of cable is more difficult to pull to the top of the building because it has this section of cable hanging off the end of it, which has weight. And the more cable that we pull in, well, the less weight or the less force is required to pull in the remaining section of cable because it doesn't weigh quite as much. So we see that discrepancy here in parts A and B, why it takes so much more work to pull in the first 10 feet of cable as opposed to the remaining 20 feet to get all 30 feet of cable.